Greetings, my name is Professor Duke Orata. We are continuing with our lectures in thermodynamics. And today we want to look at radiation. We want to look at radiation, the intensity of radiation, and how it relates to the surface temperature. Its intensity and surface temperature. So, we are continuing our lectures in radiation. I continue humbly requesting you to look at our earlier lectures. It helps build up systematically the concepts and the processes. And so we want to look at the intensity and surface temperature. So if we consider strip in this hemisphere, we consider this strip in this hemisphere which is displaced some angle phi from the normal, and that is subtends an angle d phi on A, dA. So let's have our sphere again, hemisphere. Radius, we say it is R. It's our hemisphere. IN. The dA. And we are saying that we have this strip is angle phi from the normal, and it subtends an angle d phi on dA, So let's just set down something. We're saying that we have a strip subtending, we have a strip angle phi from the normal and subtending an angle d phi. dA. And that we can illustrate there. Now, the solid angle subtended by this strip, if you remember from our earlier lectures, the solid angle subtended by the strip, remember our early angles where we had some volume element dA1 and dA2. We say that, for example, that area element dA1 subtended an angle dA1 over r squared, the other one at A2 subtended an angle dA2 over r squared. So the solid angle subtended by the strip on dA is given by W, which would be 2 pi r sine phi r d phi over r squared, And if we look at this, we can eliminate the r squared. D phi, d omega, the 2 pi sine phi d phi. So the total energy which flows through this strip, this strip, just like when we did our calculations in that earlier lecture on the total energy which flows through the area element dA1 and the area element dA2. So the total energy which flows through the strip total energy which flows through the strip Q, that's a better pen, which flows through the strip will be given by Q the energy which flows through the strip, will be given by QB, and that will be given by I phi d omega dA. And we know from Lambert's cosine law, remember we had this in polar coordinates. I phi is equals to In cosine phi. That's from Lambert's law, and it's in polar coordinates. We know that I phi is given by In cosine of phi. So we can apply that there. So that Q is In cosine phi. And remember, we have the angle subtended, the solid angle is 2 pi sine phi d phi dA. So very simple. So we just talked about angle subtended. We know how we compute that. We know what the Lambert cosine law is relating in terms of the intensity at the normal and at some angle phi. So if we are just putting that is I phi. Remember, that's just I phi. So QB will be intensity of cosine phi, not theta. I'm used to theta so much. Cosine phi 2 pi. So I can have 2 pi and just reorganize the thing. Let me have reorganize the thing properly. 2 pi In cosine phi sine phi d phi. I have dA there, so dA, you just get it there. Phi. So, when you want to look at the total energy over the whole hemisphere, it would simply mean integrating the quantities. So we have Q, B, will be the integral of 2 pi dA In integral 0 to pi over 2 cosine phi sine phi phi. If you look at the trigonometric tables, then you will see that this can be simplified to a half sine 2 phi. So just go to the trigonometric tables, you'll find that can be simplified as a half sine 2 phi. So we have Q B is equals to 2 pi dA In pi over 2 0 half sine 2 phi d phi. And this reduces simply to QB is equals to pi dA IN. And so if we combine this with the Stefan-Boltzmann law, which we saw in our earlier lectures, where we had said that the relationship in terms of the energy that's emitted to the temperature is that energy, Q, is related to the absolute temperature raised to power 4. So from Stefan Boltzmann law, Q B is sigma power 4 dA. Remember, we talk of rate per unit time in unit area, but now we are talking of rate per unit time. So we have area appearing there now. And so we equate both quantities. So equating the two quantities, we have pi dA IN is equals to sigma T4 dA. Remember, that is the sigma is the Stefan-Boltzmann constant. So what do we have? We now have pi N is equals to sigma or its density from the normal is sigma power 4 over pi. That's a very important result. So in other words, you are able to relate the intensity to the temperature of the emitting surface. In this case, talking about the black body. And remember, we mentioned that the black body, in the case of a black body, the absorbed energy divided by the total incident energy is 1. So it absorbs everything. Very important to remember that. Remember, we had talked of rho plus alpha equals to 1. That was the transmission, that was the absorption, and that was the reflection. That's the reflectivity, transmissivity, and then absorptivity. And we said that in most of the materials, this is 0. So that rho plus alpha is 1.00. Most of the materials, transmissivity is 0. And so we have that. And we have said that in terms of the absorptivity, that alpha, remember, is the ratio, the absorbed energy over the total incident energy. Always remember those things. It's important that you build the concepts systematically, so that when you apply them, you are able to apply them with a lot of ease and in a relaxed manner, because you understand what that concept is. So we have that relationship. Now, when we have these emissions, they are electromagnetic waves. These are electromagnetic waves. And like we mentioned, there were two fundamental concepts we talked about, that the intensities are not the same in all directions, and the waves, the electromagnetic waves which are emitted, are of different wavelengths. And that's what we focus on. So that these emissions are electromagnetic waves. They are at different wavelengths. There are different wavelengths. So you can lump them in a group, in a group, you can group them, those wavelengths, you can put them into different you can confine them to different regions, but they are different wavelengths, and so they have different frequencies, and they have different frequency. They have different frequencies. That is that. And this frequency is related to wavelength as c over lambda. And that's the propagation velocity of the wave. That's the propagation velocity of the wave, which normally in meters per second. And that's the propagation velocity. C is the propagation velocity. And that's the wavelength. So these electromagnetic waves have different frequencies. They have different frequencies. And this is captured in Planck's law. Where we have the relationship between these energies is such that we have that wavelength, this relationship to the surface temperature, lambda T minus 1. So it relates the energy emitted to the surface temperature. This relates to the surface temperature. T. And so if you look at this quantity Q, it is related to that band in which you have those wavelengths occur, fall. And QB, let's say QB, is related to the band. And this band here, that relationship between the total energy and the band in which you're talking of, that wavelength band, that K there is monochromatic. What we call there, that constant there is called the monochromatic emissivity. It's a constant. And so when you plot this quantity, that quantity Q by lambda versus lambda, then you will find that you have this is your lambda max. And this lambda max, you will find that when you do these values at different temperatures, you will find that as you increase the temperature, the lambda max is displaced towards the shorter wavelength. Notice that on plotting versus lambda, it is observed that lambda max shifts towards shorter wavelength as the temperature increases. And so you can actually show that. So that let's say this is some temperature T1, let's say that's at some temperature T1. What will we have? Let's say we have some temperature here, going to higher temperature. So now we want to illustrate that. So they say temperature T1. They say that's temperature T2. Temperature T3. Temperature T4. T5. T6. So we are seeing that the lambda max, let's call that lambda max 1, lambda max 2, lambda max 3, lambda max 4, lambda max 5, lambda max 6. And we are seeing that they are being displaced towards the shorter wavelength. They are being displaced towards the shorter wavelength. And in most cases, it's actually found. It is actually found that this obeys what we call Wien's displacement law. Wien's displacement law, where that lambda max times the temperature found with some constant 0.2 is related that manner. The lambda max, in other words, your T will be at 0.002 over lambda max. So it's very important to note that as you move to higher temperature, the lambda max shifts to shorter wavelengths. So let's stop at this particular point. We are continuing with our lectures. Thank you.